Hi folks, I'm Vanessa Sochat, and today we're going to be talking about Kubernetes and HPC, the bare metal bros. So I thought I would open this talk by putting two words on the slide that are either going to make you very angry or very anxious. Those words are cloud and HPC. So probably the question on everyone's mind is, what does the future look like? I'm going to answer this question by posing a question back to you. Where is the money going? So we can look at polls from Gartner and Hyperion Research that suggest that cloud is projected to reach greater than $1.1 trillion of revenue by 2027, with a 20% compound annual growth rate. HPC, on the other hand, is projected to reach $40 billion by 2026, with a smaller CAGR of 6.4%. So very superficially speaking, the money is going to cloud. Now we can also then follow up with this question like, okay, that's great, but who's going to get left behind? We can look at a paper from Reed, Gannon, and Dagara from 2023 that identified some really interesting trends. For HPC, it suggested that the way that we design our systems will not continue to work. We cannot depend on Dennard scaling and Moore's law. There's increasing rising costs for improved semiconductors. This is going to make it harder and increasingly more expensive and laborious to deploy new systems. And they define something called NREs, or non-recurring engineering costs, that we are incurring for every new system. Now, cloud, on the other hand, is leading the space of innovation. As we know, there's this massive expansion of large-scale commercial clouds. They are not depending on software vendors or hardware vendors. They're making their own stuff in-house. And they are, guess what? They are hiring away and attracting the talent pool. And they made a really interesting analogy with temperature. They described HPC as endothermic, requiring the absorption of heat for survival, and cloud as exothermic, really giving off of heat. And guess what, folks? We're not talking about heat here. We are talking about money. But to continue the heat analogy, you'll know that if you've ever been out in the snow in a cold environment, you are much more likely going to be wanting to give off heat to survive. So who gets left behind? Well, the person that needs to constantly absorb heat that's probably going to run out is going to be the one. So this is why we've been so vocal about this idea of converged computing. It's because we need to ensure that the needs of our science are represented in this new environment. And guess what? The success of our science, the reason that we're all here, really depends on our ability to be collaborative in this space. And so this is really kind of the manifesto of converged computing. We have these two beautiful spaces of technology. HPC is great at performance. Cloud is great at many other things, automation, modularity. And when we bring them together, we get this new technology space where we have the best of both worlds. So where do we start? Well, here is how the talk is going to proceed today. We're going to start with models for convergence, talking about patterns for bringing together traditionally disparate environments. We're then going to move into strategies for convergence. So designs that I've noticed allow for easy movement between the spaces. We're then going to talk about examples, so explicit projects that we're working on that best exemplify these two things. So let's start with those models for convergence. Now, if you've looked in Paperland, you've probably seen many different models. There's many different ways to take HPC and cloud and put them together. I'm going to talk about the high-level patterns and from the perspective of someone that's maybe deploying a system. So let's say that's me, and let's say I say, okay, I want my cloud and HPC. I'm going to take my limited set of resources and I'm going to try to split them between two setups. So I spend a ton of money and I do this, and then, I chose poorly. No one's using half my resources, and oh my God, so 4 years later, I come back and I'm like, all right, I want cloud X or HPC, exclusive or HPC. I understand I can't have my cake and eat it too, so I am just going to choose one. We've used HPC for all these years, bread and butter. This is the way we've always done things. I choose HPC. Great, 6 months later, someone comes into my office. Are we dinosaurs? You know, everyone over there is using YAML and automation, and we have this old setup, and so you go back in your office, you contemplate your life choices, and you're like, all right, no, it's okay. I'm not going to wait another 4 years. I'm going to sneak it in. So this is where you see all of these ideas like bursting, multi-cluster, and these are generally referring to this idea of having some home base of resources and reaching out to get more. And the problem with this approach, as I see it, is that the complexity of these approaches often reflects the complexity of the systems. So they tend to be snowflake, they tend to be complex, and this is why there hasn't been like a single leader that has emerged in the space. So here is a different idea that's less common because it doesn't superficially kind of make sense. I want cloud or HPC, meaning I want to be able to run HPC or cloud or at the same time or something together that's more converged. Like, what the heck am I talking about? Don't worry, we'll talk about it. Let's first talk about strategies for convergence. So these strategies, I need to point out, these are not just about the technology, they are also about the people, which is often harder. The first is common goals. In order to get two different communities working together, they have to care about the same things. You can't get around that. The second is modularity. So the degree to which your application or infrastructure can be modular, that's going to empower you to use things interchangeably and swap them and be very creative. The third is integration. This is consumption of an entire thing in another thing by way of different strategies. So let me give you some examples. For goals, the best overlap of goals I've seen is with respect to batch workloads. So a few years ago, the Kubernetes community started the batch working group, and this was because of this new need to have AI ML workloads in Kubernetes. Traditionally, Kubernetes is where you run services, you keep something running, and there wasn't this concept of starting something and having it complete, but all of a sudden there was this new need, and guess what? We have been doing that in HPC land for like a couple of decades now. Modularity, a really great example, is actually with Kubernetes and Flux framework. So you may think of Flux as just like this workload manager, but actually it's called a framework because we assemble many different components together to assemble into the workload manager known as Flux. Kubernetes is the same, different set of components, and there is going to be a creative way that we can kind of use these interchangeably. So the final example of integration, the best technologies I can provide are containers and language bindings. Container technologies are literally this vehicle to let you move between spaces, and language bindings are going to let you take a traditionally like C++ HPC project and extend it into a language that is native to cloud. So for example, Go. Alrighty, let's get into some examples, just like eggs, 3 ways. Here are some projects that we've actually been working on at the lab. The first is Fluence. As I alluded to, this is the Flux scheduler swapped with Kube scheduler. The next is the Flux operator, the entirety of Flux framework implemented inside of Kubernetes. And then the namesake of this talk, the bare metal bros, Flux and Kubernetes working side by side. So let's start with the Flux scheduler within Kubernetes. You may be familiar with Kubernetes. When you launch a job, you ask for a certain number of resources. That's given to the scheduler. The scheduler says, okay, here are 4 pods. Have a nice day. So what we're going to do is bring in Fluence. So our C++ package, Flux Sched, that is mapped with Go bindings into a custom scheduler plugin. We're going to swap it. And so you're basically going to be asking for the same amount of resources, but the scheduling is going to be done by Flux Sched. How does this do? Well, we find that the workflows run 3 times faster. So what you're seeing here is Kube Scheduler on the top, Fluence on the bottom. You see a lot of randomness with respect to how Kube Scheduler places jobs. What this leads to is a pathological scheduling pattern. So anywhere you see a red box on there, that is a startup delay. And what that means in practice is that although the workloads themselves run in similar times, we have a lot of outliers. We have a lot of jobs that take a really long time to get started. And so Fluence improves upon this. So Fluence is a really great example of modularity because we're taking an HPC technology and we're literally swapping it. And the modularity of the software allows for that. It's also a great example of integration. Because we have those Go bindings, we can speak the language of the cloud native communities. Alrighty, next project, the Flux operator. He's super cool. All the Gophers in Fluxland are pretty cool. Alright, so the Flux operator is implementing the entirety of Flux framework inside of Kubernetes, your own HPC cluster. This happens by way of a custom resource definition or CRD, where you basically give all the parameters that you want for your cluster, whether that's a single job or whether you want an interactive cluster. This creates what we call a mini cluster, which, Flux doesn't know the difference that it's running in Kubernetes versus on bare metal. There's a lead broker that's connected to several follower brokers. So here you have 1 pod for 1 physical node via tree-based overlay network. Within each pod or node, you have Flux that's added on the fly to your application. And the operator is just going to basically reconcile until the state that you need for your cluster matches the actual state of the cluster. How well does it do? Well, we compared it to the best in the space last year. The MPI operator and the flux operator consistently outperformed the MPI operator, we believe, because of the 0MQ bootstrap. So the Flux operator is a beautiful example of integration because we're taking the entirety of Flux framework and implementing it inside of Kubernetes. Bro, is it time for the bare metal bros? Yeah. Okay, so warning, I've been saying bare metal, but nobody's going to give me bare metal. Let's be frank about that. So I was using virtual machines. We're using virtual machines as a proxy for bare metal. So just a warning. So what's different about this picture? The orange is on the outside. So we actually have Flux framework on the outside spinning up a Kubernetes cluster. And notice that we actually still have compute running on bare metal alongside Kubernetes. How's that possible? Don't worry, I'll tell you. So why do we need this in the first place? As you know, also, there are increasingly more complex heterogeneous workloads that are coming to HPC. So this means not just, embarrassingly parallel stuff, but also adding in services, databases, task queues. Okay, so this slide is not wrong. I was going to give you an example of such a workload, and apparently the slide is giving you this warning that I'm a bad scientist, and it's not wrong. But I will point out that my example is actually a very good example that is a prototype for this kind of design. Let's talk about that. So let's say that we're running simulations. We're training examples 1 through n, whatever, doesn't matter. And we want to send them to a machine learning server, a specific endpoint to do the training. We then want to wait till some metric of goodness or perhaps a number of samples. And then we want to flip it around. We want to run simulations again, but we want to instead give this to our machine learning server without the actual values. Then we're going to have a vector of the true values and the predictions, and we're going to see how well we did. Now, very superficially, if we mapped this to HPC versus Kubernetes, this is how we do it. We would expect that the simulations would run better on bare metal and the service thing would run better in Kubernetes or Kubernetes. This is we need to prove to ourselves first. So a lot of you are probably out there like, Kubernetes, like in user space, are you nuts? I'm not nuts. There's actually something called Kubernetes. It was a Kubernetes enhancement proposal, or KEP, proposed in 2022 by a very talented developer named Akihiro Suda. Akihiro, I must point out, won the top maintainer award for KubeCon last year. He's an incredibly talented developer. If you've used any of these technologies, he's the one behind it. Hats off to Akihiro. So last year, at the beginning of the year, Kubernetes was really a hodgepodge of kind of bash scripts. It was really hard to use. So I engaged with Akihiro and we released generation 2 of Kubernetes in September. And guess what? It is using containerization, which is really great. It has these components that we'll go into in more detail. So what does it mean in practice? Well, it means when you're building a virtual machine, you need to have cgroups version 2 enabled. I recommend Lima or Linux virtual machines if you're prototyping this for the first time. It also means that you need to enable these kernel modules. So very generally speaking, VRNet filter is going to allow you to apply IP tables rules to bridge traffic. And VXLAN is going to allow you to connect VXLAN devices on different hosts to a standalone bridge. This is important because we actually have different physical nodes. Now it's going to use rootless Docker. This isn't such a crazy idea anymore. Many clusters have Podman these days. And so what does it mean? Actually, when you're bringing up these VMs, it means that you're going to run a make up command that has 2 contexts. So both of them are going to build and start a base image that is using kind, Kubernetes, and Docker with CNI plugins. And then the 2 contexts are the control plane and the worker. The control plane is going to install Flannel, run Kubernetes init. This makes a join command, which is basically a token that you give to the workers, and then the tokens can authenticate and join the cluster. That's all they do. They're just like, I'm ready to serve. Alrighty, so we created the Star Trek cluster, small and mighty, using Overt and Ansible. It is small and mighty because each has 8 cores and 30 MBs RAM and a 10 gigabit Ethernet. And I want to point out that we have 7 nodes here because generally speaking, we're going to have 6 that we run things with compute on, and one's going to be an admin node or a control plane. Again, warning, not bare metal. You get the deal. Alrighty, so what's in these VMs when we bring them up? Well, we have a complete system install of Flux. Singularity on bare metal for reasons I'll tell you in a little bit. Lamps installed on bare metal, and of course, Kubernetes ready to be brought up. So once I shell into these VMs, my Flux cluster is ready to go. I can do Flux resource list, and I can see all my nodes. And Kubernetes, again, that administrative node is also a control plane. So we technically have 6 nodes to work with, and we can still see them with kube control get nodes. Here's what we're working with. Kubernetes and Flux running side by side, the bare metal bros. All right, bro, what experiments do we want to run? All of them, bro. All right, so we first need to sanity check that what I said earlier about the bare metal and lamps and the simulations is actually true. We need to look at application performance between Flux and Kubernetes. So the way we're going to do that is by running a few things. We're first going to run lamps on bare metal with Flux. We're then going to do the same thing, but in a singularity container. And I did this just to demonstrate that you don't lose anything by using containers. Containers are great. We're then going to run lamps in Kubernetes with the Flux operator. And then finally, we're going to repeat cases 1 and 2, but with Kubernetes running in the background to look to see if there's any overhead of that. And I need to pause for a second and point out how incredibly cool this third case is. We have Flux on the outside. Flux is running Kubernetes, Kubernetes. Within that, we are launching the Flux operator, which is bringing up another instance of Flux. And inside there is where lamps is running. So folks, like, I know Thanksgiving is over, but this is the ultimate turducken. And we expect lamps to be slower in Kubernetes because, as we know, it makes MPI collective calls. Kubernetes is using something called slurp4net-ns, which requires additional processing of packets with a tap device. I have a great paper I can share if you're interested in learning more about that. So drum roll the results, as we expected. Well, actually, maybe we didn't expect, but guess what? The bare metal case is the singularity container is very comparable to actual bare metal. I was very surprised by this. So Kubernetes does not add a lot of overhead. And this is what we'd expected. That guy up there running in Kubernetes is about twice as slow as running on bare metal. So what did we learn? Well, we learned that for a setup like this, the network sensitive stuff probably should be run on the HPC. But I'll point out there's opportunity for improving this in Kubernetes. If you have experience with networking, I'd like you to go over to the GitHub right now. No, I'm just kidding, wait till after the talk, and engage with Akihiro to work on this problem. Now, the next thing we wanted to look at is distributed machine learning, specifically 2 cases, one distributed, so across 6 nodes, and then the second on 1 node. So the distributed case, network is a variable, and for the 1 node, obviously network is not a variable. Drum roll results, same thing. It's about twice as fast on bare metal, or twice as slow, I guess, on Kubernetes. And interestingly, when you look at just a single node, these are really comparable. So there's no issue with running something on a single node in Kubernetes in and of itself. It's really when you bring in the networking that it becomes a variable. So it's a network, right? Well, let's sanity check one more thing. Here's iPerf thing. We did 1 minute of transfer for each node as a client to each node as a server. We see bitrate in gigabits per second is between 10 and 30 for bare metal. Kubernetes is like not detectable, close to 0, really, really terrible. We can see the same patterns for transfer gigabits per second. And so yes, it's the network. We're pretty confident for the setup, it's the network. All right, can we do the fun workflow now? We absolutely can. So guess what? I actually prototyped this kind of workflow because I was really excited about it. And so what we're going to do is we're going to be launching a batch job with Flux Batch. This means a Flux instance that's owned by the running user. It's going to scope resources using HWLock. In this batch job, we're going to basically bring up and tear down all of Kubernetes. We're going to take that workflow that I mentioned before. We're going to map it into our Star Trek cluster space. So we're going to run simulations with lamps, randomly selecting the problem sizes to predict wall time. We're then going to bring up a machine learning server, a special server I made using River a few years ago. And then we're going to basically do the test cases. We're going to run lamps again, but we're going to leave out the actual wall time, and we're going to ask our models what it is. And we're going to do 1,000 training samples and 250 testing samples. How did we do? Okay, so I put no thought into these particular models, but I did 3 kinds of regression. The Bayesian and sampling from a probability distribution didn't do super well. But for the first 2, there's an actual kind of pattern between the predicted and the actual time. And so although I put no thought into this, I was really pleased with this result to see that the general prototype this idea of having bare metal simulations running alongside a service, there is something here. We can do science this way with actual real scientific questions. And I'll point out that there are real heterogeneous workloads out in the wild that need this capability. Here's MUMI, the massively parallel multi-scale machine learned model infrastructure. And this is basically simulating biological systems, the interaction between proteins in a plasma membrane. I'll also point out that the Moomins are what it's based on, the name, a Finnish comic book series with really cute hippos with often yellow spiky hair. Very awesome. So this is a perfect example, the bare metal bros of coexistence, adopting technologies to make it possible for them to coexist and continuing to improve upon them so that, for example, with networking, this environment can get even better. So what should you remember from this talk if you take nothing else away? The first is looking out for opportunities for collaboration. Look for that alignment of goals between spaces. That's an opportunity. The second is providing handles for your components. So if you don't have the bandwidth to look for opportunities, add some Go bindings to your C++ project because someone else could find you. The third is engagement. We need to show up at the table. We need to go to working groups, conferences, places that you haven't traditionally been to engage and to find these opportunities for collaboration. And possibly the most important is this mindset. We've had this mindset of cloud versus HPC, that one has to win, that they're different for so long. We need to throw that away and get rid of the adversarial thinking and have a more collaborative mindset. This is the vision that we have for the future for converged computing, and we hope that you'd like to join us. So thank you. That's how to reach me, my email and social networks. And here's some interesting links for the Flux and the various projects. I think I will take some questions virtually now.